So, I can open up 340 too. CSCI. If the idea of writing the report is intimidating, first of all, I'm not saying you're wrong, not at all. It definitely could feel that way. But this is technical writing. It's not like writing essays or anything. It's technical writing, and it's a very different style of writing. And in my opinion, it is hilariously easy relative to like writing essays. And it's because with technical writing, you don't need to worry about being like fancy with the way you write. In fact, if you are, people will get mad at you. Technical writing is basically 1 degree away from being point form. In fact, this is my recommendation to you when writing your reports. This is how I write every single paper I ever write. This is how I do it. Is I start by coming up with a general idea of how I want the paper to be laid out, you know, like your introduction, maybe a little bit of a literature review, explain the data, right? And then based on what I've done, I will just put in point form in each section what I want to hit. And then I'll go to the next section and do it. And chances are, 9 times out of 10, as I move to the next section, I think of another point to hit in the previous section. So I just keep adding points. And once I have all my point form points, I'll go back to each section, and maybe I'll order the points in such a way that there's like a nice flow to them. Like it makes sense to talk about, like within the introduction section, it makes sense to talk about this and then this. And we definitely want to talk about that before that, though. So just kind of order them. Then I turn those points into sentences, and then I just combine the sentences into paragraphs. It's basically point form, but just not point form. Further, you write about what you did. So if you did a bunch of analysis, you're not going to be running out of ideas of what to write. You just write about what you did. So technical writing is relatively easy compared to like writing fancy essays or anything. So if the report's intimidating you, okay, but make sure you're going at it with the right mind, like the right frame of mind, because it might simplify things for you. It might make it not seem not so bad.
Writing in late text is not mandatory?
It's not mandatory, but you're giving up those sweet points, right? Yeah. In my opinion, so the first time you do LaTeX, LaTeX, people call it everything. I've heard people call it LaTeX. It's weird. That one I know is not right, but the first time you do it, there's a bit of a struggle. But after you do it once, people tend to find it's way easier to do it there than in like Word. Because Word, just getting things formatted the right way and a right template and everything is very difficult to do in like Microsoft Word. But in something like LaTeX, where it does all of that like formatting and typesetting and everything for you, you don't even need to think about it. You just write text, and it just kind of makes it look pretty for you. It's nice. All right. Okay, we were talking about these things, Turing completeness, the invisible hand, learning to walk. This is basically where we were, right? And last time we kind of ended with the idea of like, beware of teleology. Explaining things in terms of their utility as opposed to actually how they came to be. Nothing exists for a reason, with the exception things being like designed and engineered by humans, or I guess any other creature if they made a tool or something. But nothing in this universe exists for a reason. It's just there. And the reason it exists is because it doesn't not exist. It's just there. It didn't cease to exist at some point in time in the past. It doesn't exist for a reason. Even things that exist for a reason are still subject to these pressures of like evolution. Evolution has no intelligence guiding it. There's no intelligence. Now, when we're doing it, when we're harnessing these ideas for evolutionary computation, there is some intelligence. We're using fitness to guide the search. But at the end of the day, evolution as a whole has nothing guiding it other than those powers that are in conflict. An increase in diversity and a decrease in maybe I can word it better. There's those variations that'll happen, which can increase diversity. And then there's also selection pressure. Things that are good might lower diversity. But these two forces are at odds with one another, and that's kind of where you get this emergence of evolution. In spite of nothing guiding evolution, here we are. There was nothing there, nothing pointed in the right direction. There was no intelligence behind it, yet here we are. Things work because if they didn't work, they wouldn't be here. That's it. If Google had a terrible business strategy, we wouldn't be using Google today. But I guess their strategy was good enough. And that's another thing about evolution. It's not necessarily about what's good, it's about what's good enough. It just needs to persist. That's all it needs. Learning to walk. I think I already hit this example before, and then you were talking about the swimming instead. Consider the problem of training a robot to walk. Deep learning, terrible way to find the best way for a robot to walk. It's a terrible idea. So here's what was up with deep learning. For those of you that don't know, let me know if I told this story already. You know, it's funny in like science or just really with anything. There will be things that everyone says, that's a terrible idea. That's a really bad idea. It's stupid. Why would anyone do that? That's stupid. And then finally, someone comes along and shows that, no, maybe that stupid idea was actually a really good idea. And then immediately everyone flips and goes like, well, obviously that was a good idea. Everyone knew it was a good idea from the get-go. This happens a lot. And deep learning is a good example of this. Deep learning is a terrible idea. Here's why deep learning is a terrible idea. And I'm not just talking about learning to walk. I'm talking about, for any given problem, deep learning is a terrible idea. Because when the algorithm is learning, it's updating those weights, right, in your network. Raise your hand if you're familiar enough with deep or like neural networks to know what I mean by weights. Okay, most of you. But basically, a neural network is this network. Just think of like graphs. And each edge has a weight associated with it. And those are being updated by the learning algorithm. As you add more and more and more and more and more layers, as you make your networks bigger and bigger and bigger, the number of weights that need to be changed grows. The problem is, if we now have like hundreds, thousands, millions of weights to train, to tune, there's no way you're going to find a good configuration of weights. It's not going to happen. It's just, there's no way. It's too hard of a problem. But deep learning seemed to have worked for two reasons. One, you got to use a hell of a lot of data when you're using deep learning, right? If you've got a small little problem and you throw deep learning at it, people will laugh at you. People will make fun of you, and they should. But we have a lot of data. But there was this realization that, well, hold on. I don't need to find the best configuration of weights for my network. I need to find a good enough configuration of weights for my network. And it seems as if as you increase the number of weights, the number of dials you can turn, that your algorithm can turn to fit the data, as you increase the number of dials, you increase the number of good enough configurations. And suddenly, deep learning was, holy shit, this is working really well. Now, all of the most sophisticated, fancy-ass machine learning we have today is all based on deep learning. Which was a terrible idea. You go back 20 years, Geoffrey Hinton was an outcast. People wouldn't sit with him at conferences. He was that kook that thought deep learning was a good idea. What a fool. Now he just gets to show up and give everyone the middle finger because he was right. Okay, yeah, I think I just explained it. Yeah, the best. And this gets to my point of when I'm looking for the best way to walk, like all of you have an encoding. In your brain, in one way or another, there is some encoding of how to walk. If I told you all to stand up, take a couple steps, all of you have something in your brain that tells you how to walk. How it looks like, I don't know, who cares, but it's there, because you can all do it. But we've all tripped. Did anyone trip up the stairs today even? You know, like it happens all the time. So we actually probably all kind of suck a little bit at walking, but it doesn't matter. We don't need to have the best configuration. None of us in here probably has the best encoding of walking in our brains. And for some problems, is that even a valid question? So for some problems we say, I don't care about the best, I care about good enough. If it does the job, it does the job. I'm happy, I don't care. And then maybe for other problems like walking, is there even such a thing? You know, humans, we are so obsessed with designing things and engineering things and understanding things that it's a natural thing we want where we're like, yeah, but I want the best one, right? We're optimizing for TSP. I want the best one. I want it. Why? Because that's how we are. We're obsessed with that type of stuff. But for some types of problems out there, does that even exist? Is that like an idea that's doomed to fail, going to look for the best configuration of walking? Maybe it exists, or maybe it doesn't even exist. Maybe there's no such thing as the best way to walk. Maybe that's a stupid question. I don't know. At the end of the day, we can train robots to walk. Why? Because they learn, and it's good enough. It's good enough. Any questions about that? Now, the whole point of this topic, I mean, this topic ends up being a little bit more hand-wavy. It's not particularly technical of a topic, right? But here's what I want you to do for next class. And really not just for next class. I want you to be a little bit aware. I want you to just spend time thinking. There's no assignment here. There's nothing objective to complete. I just want to make sure that, you know, every once in a while you take the time to think about, hell, you're sitting down watching baseball. And you think, you know, baseball's got this set of rules. How did they land on these set of rules? I mean, the set of rules, it's a system. How did they decide on these sets of rules? How did baseball even become baseball? How did that start? The game exists today. It didn't pop up out of nowhere and exist in that form since day one. No. How did it start? Did it start by just people playing catch? And then someone's like, oh, I bet I can hit that ball. Right? Like, is that how it got started? I don't know. But how did it become into existence? And how did it get to where it is today? You can play this game with anything. Try to, you know, think about it. Football, like North American football. You can see its relation to rugby. If you're familiar with watching, raise your hand if you're familiar-ish with rugby. Raise your hand if you're familiar-ish with North American football. Okay, we got like one person in here.
Computer science.
All right, fine. But you can see they're different games. They diverge and they evolved in their own directions. But when you notice that, it becomes interesting to think like, well, how did we get there in the first place? And how did one become one and the other become the other? It's kind of wild. Just, I don't know, spend time thinking about this. All right. So now that we're, what, are we like 3.5 weeks into the semester? 3 weeks in? I don't know. How far are we, what week is this? All right, if you don't know and I don't know, we're fine. Now that we're this far in, I can finally give you an overview lecture of evolutionary computation. Finally. Here's the idea. Given a population of individuals within an environment with limited resources, competition for those resources is going to happen. This competition causes some form of selection pressure. You know, we might call it natural selection, but there's going to be, because there's this competition for resources, there's got some mechanism of selection is going to happen. Why did that monkey get the banana? Because it fought the other monkey and it was stronger and it got the banana. I don't know, that's a silly example, but there's some fitness, there's some selection mechanism. And this selection mechanism will, overall, the fitness of the population within the environment will, on average, over time, improve. You have a population of things, some are better than others. Those that are not as good will die off, but they got to be replaced with something, and there's still competition. So there's always this arms race. And you got to remember, the arms race doesn't exist between just humans. It exists between humans and everything else in our environment. So there is this evolutionary arms race. In the context of evolutionary computation, given some problem and a mechanism for measuring solution quality, this is the problem, this is the environment for the evolution. Generate, if we're using a fixed size population, which you don't have to do, given a fixed size population, well, competition's going to arise for which chromosomes will exist within that population. There's a fixed number of seats available. Some aren't going to make it. It's the way it is. So this is the limited resource. We're going to apply some quality measure, and those that are more fit are going to be more likely to reproduce and fill up the next generation. The more fit individuals compete better for their seats. And that's that. I already showed you this image. This is all of evolutionary computation. It doesn't really matter which form of evolutionary computation you're doing. They all follow this general idea. A GA is perhaps the most overtly obvious one. If we start looking at things like particle swarm optimization, this figure might feel less relevant, but it's still there. All forms of evolutionary computation more or less follow this idea. There's a population, there's limited resources, competition's going to arise, and some are going to win out in that competition, and some are going to lose. And overall, that helps the population. And it's always interesting. I know I've emphasized this a lot already this semester. Changes will happen to the individual, and individuals are acting selfishly all the time for their own best interests, but we often like to think of populations evolving together and not just individuals. And it's kind of hard for us to kind of get that mentality because we're all individuals, right? But really at the end of the day, it's a population as a whole that's changing and moving. Hopefully that kind of makes sense to you. There are two big factors at play: variation. Genetic operators like mutation and crossover, they increase population diversity, and this pushes the population towards novelty. And this is a really good thing. This is a very good thing. We like newness in the population. Newness is very important for a lot of reasons, both in terms of biological evolution and evolutionary computation. Newness is how the population can explore the space it exists in, that novelty. And then there's selection. Things surviving within the population, this decreases diversity. If you have really high selection pressure, those that are really fit, on average, as a quick and dirty heuristic, if you have a population and you take all the candidate solutions with similar fitness values, often they are very similar candidate solutions. Not always, but that's a pretty easy heuristic to use. So if highly fit individuals are more likely to make it to the next generation, way more than those that are not quite as fit. And remember, fitness isn't, I'll come back to this. If selection pressure is too high, we can destroy diversity, and the population is going to stagnate. It's going to get stuck. It's exploiting what's already good, but it doesn't really have a good way to push to newness, and that's a problem. We don't want evolution to stagnate. If it feels like, well, fitness is what guides the search, yes, it is. And if you think, well, fitness is the most important thing, it's the most important. No, it's not. Absolutely not. Fitness and diversity, these two things, selection and variation, that's what it is. They go hand in hand for the population to evolve. Fitness, having a high fitness, okay, that's a good measure of an individual. But that's not good for the evolutionary process. That's not good in the long term. Don't get so focused on fitness. So, if one thing hasn't been obvious so far, when I told you to make your GA and you tinker with it, I'm telling you, like, sky's the limit. Do whatever the hell you want to do. It doesn't matter. All that really matters is that you follow the high-level framework. And given the high-level framework, even in terms of something as simple as like the specific type of algorithm, like the GA, given that evolutionary computation is such a high-level framework, there's so many different variations. Some people argue, really, they're all just variations of GAs. I don't quite agree with that. A lot are. But there's a lot out there. All of these forms of evolutionary computation, they're population-based iterative processes where they've got some selection and variation mechanism. GA, it's not the first form of evolutionary computation to pop up, but I'm confident in saying it is by far the most common and widely used. But these typically, I'm always qualifying everything with like typically, because again, there's no hard rules on any of this stuff. Typically, you have like a string or an array list encoding, some linear encoding for your problem. The binary string, it's a binary string. TSP, it's TSP. That's not to say you can't have more interesting or complex representations, but typically you're seeing that. You've got your crossover, you've got your mutation, you've got your selection, there you go. Evolutionary strategies is a different type of evolutionary computation. And that one's designed to work really well with real numbers. You can use genetic algorithms to work with real numbers, but they tend to not do as well as some forms of evolutionary computation that are kind of designed with real numbers in mind. There's another one, differential evolution. This one's kind of popular. It's great because, excuse me, it works well with real numbers. And what's interesting about this one, and perhaps I've always kind of thought it had a funny name, is the problem space that you're looking at doesn't need to be differentiable. There doesn't need to be a gradient for it to work well. There doesn't need to be like a guiding slope to guide the algorithm in a certain direction. So I always thought, shouldn't it be called like non-differential evolution? But whatever, they call it differential evolution. Particle swarm optimization. Now, to be clear, people would call these evolutionary here. There's evolutionary computation, and a subcategory of evolutionary computation is evolutionary algorithms. And a subclass of that would be like a GA, evolutionary strategy, differential evolution. A lot of times I will say an evolutionary computation algorithm, it's like a catch-all. But people would say particle swarm optimization, that's not really an evolutionary algorithm. It's a form of evolutionary computation, though. In PSO, it works well with real numbers, evolutionary programming. What's neat about this is it actually evolves finite state machines. Raise your hand if you know what a finite state machine is. Really? Oh, man. It's just a very simple form of computing. It's a very simple definition of a computer, like the simplest form. Genetic programming, this one might be my favorite. It evolves programs, actually. And you actually, you typically, really it's just a GA. But instead of having like an array encoding, you encode things as a tree. We're going to talk about genetic programming later in the course. And with that, you can evolve programs, which is pretty cool. Any questions so far? Everyone's happy? Evolutionary computation, algorithms are remarkably modular. They're very high level, they're modular, so they can have many different components, and you can do whatever the hell you want to do. The base components of, you got your representation, you've got your fitness, you've got your selection, you've got your mutation, you've got your crossover. You can take any of those out and play around and change them for another form of crossover, that's fine. Or you can show up and be like, I want to have a new form of variation operator that works on 3 chromosomes, because why not? Cool, yeah, go for it. You can do whatever you want, it doesn't matter. You can throw in elitism. That's a new idea. It's not standard, although arguably it is these days. But that's a whole new idea. You can add whatever the hell you want to your evolutionary algorithm. That's part of what I love about them, is they're such a simple idea, and they work really well. You can do whatever you want. And what's correct is what works. So, have I used the word genotype and phenotype yet? Someone's nodding. Well, I'll say it again just in case. The phenotype, this is a word stolen from biology. You are all a phenotype. You are the manifestation of your DNA. Your DNA is your genotype. It is the encoding of the phenotype. So the phenotype is what the encoding means, and the genotype is the encoding. So if we were doing that binary string one, the phenotype space would be, well, what is the integer value? What does that encoding mean? And the genotype space would be, well, the binary strings themselves. Often there will be some form of like translation required. How do I go from the genotype to the phenotype? And depending on how complex that is, you might, people sometimes will say, well, we have a very direct representation or a very indirect representation. But those are all relative terms. You're going to have to forgive me. I got to sit down and continue lecturing. I can't pace anymore. I'm dying here. Oh, bear with me. You can all hear me pretty well still, right? Okay, good. I appreciate your patience on this. All right. Candidate solutions are the phenotype. Remember I was emphasizing the difference between like a chromosome and a candidate solution? A chromosome is an encoding of a candidate solution. A candidate solution is like the phenotype. So candidate solution, phenotype, chromosome, genotype. But people will mix these words frequently. I know I do it. And really, a candidate solution could mean the encoded version as well. It doesn't, it's more of a catch-all, but whatever. Genotype and chromosomes are words to describe the encoding. However, chromosomes are themselves candidate solutions, and candidate solution is often used as a catch-all term. So just be warned of that. Right now I'm about to throw some terminology at you. Half of this is terminology people are aware of, but no one really uses. So there's like a locus, a position, or a gene, or an allele. These are all words to mean like, if I had the binary string encoding, it would be a single value, a single 0 or 1. So what is the gene at index 7 of my binary string? That would be a gene. No one uses this jargon though. It's not really used, but it exists. So, all right, 2 phenotypes and genotypes for the unsigned binary. The phenotype is an actual integer and the genotype is a binary string. Here the binary string shown as a vector. The locus position gene allele would be a single value within the vector. So like this 1 could be the gene, but people don't really use that word. Now, so you've got a problem. You're working on TSP, let's say, and you know what the phenotypes are. The phenotypes are like the paths. Well, how do we encode it? Well, it's going to be ideal to ensure that the way we encode the problem, we need to make sure it can actually, all possible valid and useful phenotypes can be encoded in the genotype. It would be a problem to have a genotype that had a giant hole and couldn't actually ever represent some giant chunk of the phenotype space. Imagine having an encoding for TSP where, it really wasn't possible to have paths that look a certain way. Like, no, we need to make it sure it can actually represent all possible paths. Otherwise, we've got a problem. Now, that said, sometimes it's important to constrain the search space where you could say, well, my encoding can absolutely represent all possible, like let's talk about TSP, for example. My encoding could be If I have n cities, I can have an n-length array where each value is just some city number, right? That could be my encoding. You start at the city at index 0, then you go to the city at index 1, and so on, 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 all the way to the end. But it might be worthwhile to actually change what's allowed to be represented. It might be worthwhile saying, look, a correct solution has to visit each city once and only once. So instead of having a list of just a length n of where each value is just some arbitrary city value, make sure each chromosome is a permutation of the cities, where each city can only exist in the chromosome once. And it must exist once, but it can only exist once. Suddenly, we've got a much more constrained search space, which is good, and all that we've cut out from the search space was a bunch of really inadmissible solutions. I'm going to go into this example in more detail a little later, if it wasn't 100% clear. But long story short, we want to make sure our encoding can encode all possible valid solutions, but sometimes we do want to constrain our search space in such a way that it eliminates some solutions for a good reason. What the encoding should be for a given problem is not always obvious. And we'll see some examples of that. And a clever encoding can drastically improve the results of an algorithm. Fitness and fitness function. Well, the fitness is a measure of how good a candidate solution is. The fitness function is the mechanism we use to measure a given candidate solution's fitness. This is what the population is trying to adapt to. This is like what it's pointed towards. And what the fitness function should be is not always straightforward. We even saw with the binary string representation, we saw two different fitness functions. Both are intuitive, don't get me wrong. But admit, who would have admitted they wouldn't have thought of the counting ones or zeros one offhand? So converting it to an integer, okay, yeah, that makes sense. Counting the zeros and ones, well, that also makes sense, but yeah, I guess I never really thought of that. Both will be valid, but your choice of fitness function could very much affect and impact the performance of your algorithm. When you change the fitness function, you can really change the topology of your search space. When I say topology, I mean like what's adjacent to what. And that was going back to that graph I tried to draw a week and a half ago. Remember my terrible three-dimensional graph? Forget it. If counting the zeros and ones, we'll hit this later in the course. It's not too important right now. In fact, I don't want to confuse you. A population. By the way, at this stage, this should all be relatively review, right? We've all talked about these things in the context of a specific problem. Now we're talking about a little bit more general. Population is simply a collection of chromosomes. Each chromosome has a fitness value associated with it, and the population often has a fixed size, which is the limited resources that there's competition for within the population. But this is not always the rules. There are strategies. People will have variable size populations. It all depends on how we design our algorithm. And a lot of that will come down to like steady state algorithm versus generational, and we'll talk about these when we get there. Over time, if everything's going well, the average fitness of the population should be improving. And diversity is a measure of how different the candidate solutions are within the population. Now, how you measure diversity is, well, that's up to you. And as I've said several times before, it's often helpful to think about a population evolving rather than the individual candidate solutions. Even though the variations are being applied to individuals and the fitness is a measure of an individual, really it's the population that's evolving. It's all about what's good for the population. Here's an example population. If each chromosome is represented as like a vector as I've shown it here, if I have a collection of these chromosomes, that's my population. Selection. This is the mechanism for selecting which candidate solutions are going to persist. Now also remember, just because they were selected, they might have the variation operators applied to them, or maybe not. It all depends on how the dice get rolled. Remember how there was like a probabilistic chance of mutation being applied and crossover being applied? If you're selected, maybe you get copied directly to the next generation, or maybe you end up having variation operators applied to you. Whatever. Selection is stochastic but probabilistic. We want there to be some selection pressure where those that are more fit are more likely to be picked, but we don't want too much because that can really hurt the population diversity, which will just kill the quality of the population overall in the end. There are many ways to do selection. You can do whatever the hell you want. The one we talked about so far was tournament. This is a popular one. It's popular because it's simple. It's got some interesting properties that we'll dig or sink our teeth into when we get to the selection topic. But another popular one is roulette wheel. What's neat about roulette wheel is it's fitness proportional. But again, we can get in the nuance of these a little later. There's generational and steady state algorithms. For the most part, I'm going to only really be talking about the generational ones. They're a little easier and I think they're a little more common. Generational is when you have very discrete generations. Right? You do selection, you select everyone who's going to be in the next population, you apply the genetic operators, bingo bango, you've got your next generation. There's very discrete transition from generation to generation. Steady state is a little bit different. It's a little bit more complex, but it's interesting. Instead of having these discrete changes, instead what you do is you're continuously working on the same population. So if I did selection, instead of picking two chromosomes and going, okay, you're going to be in the next generation, and you may or may not have variation operators applied. What I do is I select two chromosomes, roll the dice to see if I do variation operators or not, and then I go and put them back in the same population. How I do that is up to you. Who do you replace? Do you replace the ones that were selected? Do you go and replace those that were the worst, like that had the lowest fitness? Maybe you go and replace those that are really not adding diversity to the population. Maybe you go and you replace those that have been in the population too long. They're too old, they die off, I don't know. But with the steady state algorithm, you actually need a whole other selection strategy. You select who's going to persist and have the variation operators, and then you need to select who's going to get replaced in the population. It's a very interesting style of evolutionary algorithm. So here's an example, right? I've selected B and E, and I'm going to apply the variation operators to them. And then I've also selected C and I to get replaced. Why did I replace C and I? Maybe they were just really old. Maybe they had really low fitness values. Maybe they really didn't add diversity, or maybe I just randomly selected them. I don't know. But they go and they operate, X and Y will replace someone within the same population. So there's no discrete transition in generations. With something like a steady state, it's hard to say, well, what generation are you on? Because you go like, well, it's not really a thing, right? There's no discrete generation. Any question about this one? This one can be a little funny. Remember, these are all high-level ideas. So if you're asking, well, how would I implement that, though? The answer to that is however the hell you want, because there's no right answer. Variation operators, they're used to create new but different individuals based on old ones. And depending on the representation, some variation operators may be more helpful than others. In fact, some might be catastrophically destructive and you wouldn't want to use them. It really depends on the representation and the encoding. Although it to be clear, although it really does depend on the type of evolutionary computation used, like I'm pretty sure evolutionary strategies doesn't use crossover, it only does mutation. I think differential evolution is similar-ish. I can't remember offhand. In general, there's going to be two types, your mutation and your crossover. GAs uses both. Mutation, there's this common argument in evolutionary computation that I find amusing because I will stand in front of you saying they're all wrong and I'm right. There's a common argument in evolutionary computation that no, mutation is exploitive. You take a chromosome that's known to be good, it got selected, and you change it a little bit, so you're exploiting what's good. And people go, no. Mutation is explorative. You take what's good, you make changes to it so it can actually jump to a different chunk of the search space. Then the inverse of that is crossover. Crossover is explorative because it's going to make bigger changes to the chromosome, so you're going to jump. Like imagine I had a crossover where I did like 1-point crossover where I just kind of like flip the second half of each chromosome. That's going to make a drastic difference. So it's going to throw that chromosome widely way out in some other area of the search space. And other people say, no, that's exploitive. You're taking two things that are good and you're hoping to, use that. What I say is you're both wrong and you're trying to apply a strong label to something where ultimately it depends. It depends on the search space, it depends on the problem, it depends on the encoding, it depends on what the mutation is, and it depends on what the crossover is. You can't use these words in absolute terms. And if you do, you're a fool. You heard it here. I'm calling them all a fool. Back when I was doing my undergrad, there was this giant argument. That argument took place at the university. There would be a giant flame war over this. And there I was standing there going like, you're both wrong. You're morons. You're applying these hard and fast rules to something in a world where, how do you make a GA? However the hell you want. How could you possibly have a hard and fast rule on anything where it's, how do you do it? However you want. If you go back, here's an example of a mutation that's explorative. Remember the binary string example. If I did crossover, I showed you an example where it wasn't possible, with just crossover alone, it wasn't possible to get the optimal solution. Because it wasn't possible to get a 1. Let me go back real quick so I can show you. Here. Here. On this problem, with this encoding, with this fitness measure, when using crossover, a single point crossover, pick one of these chromosomes, pick two chromosomes, pick an index. If I pick this index, flip, exchange between the two chromosomes. If this is my population, it's a small one, but it's serving a purpose to explain. It's not possible for me to ever find the optimal solution. Because there's no way for me to add a 1 to index 1 in any of those chromosomes. Crossover alone, I can't do it. There's no way to get a 1 in there. I could do every possible combination of chromosomes and apply crossover on every possible index. I can't find the optimal solution. It's not going to happen. Here, I would say the crossover is very exploitive. You're exploiting the information that already exists within the population. Mutation is explorative. It's a way to add new information to the population. But this is just one example. I could find you a million counterexamples and then a million counterexamples to those counterexamples. It all depends. These are relative terms. These are also the people that will use direct and indirect representation as if they're absolute terms when really it's all relative. It always just depends. Some representations are more direct than others. It just depends. Overview. Components. Yeah. generational steady state, variation operators mutation. Mutation acts on a single chromosome. There's an example. We changed something and it affected the phenotype. For whatever reason, that vector represents that blue guy right there. And then if I change the 5 to a 9, suddenly it gets orange arms. Why? I don't know. Don't worry about it. The point is it changed something about the 1. Crossover is different. If I took these, put them over here, and put these over here, suddenly if I have this orange dude and this, or blue and orange dude, suddenly, they inherit the traits of both parents. All right? That's the idea there. Mutation and crossover, they're stochastic. They're probabilistically applied. Depending on the operator, you might have a lot of random things to pick. For crossover, I need to randomly pick the 2 things that are going to get selected. I got to randomly select an index and then exchange them. But for other crossovers, maybe I have more randomness I need to go deal with. It always just depends. There's no hard and fast rules here. And then initialization and termination. If we go back to the image, that's all we have left. We talked about our population, our representation. How do we evaluate? How do we select? How do we apply variation? Well, how do we create the initial population and how do we end? However you want is the answer, like everything else. Do you want to generate the population randomly to start? Sure, good, cool. Maybe you can seed the population with solutions that you think are already good. Cool. That could have the downside, though. Maybe you bias the search too much, or maybe it's really good. I don't know. There's no right answer here. You try it. If it worked, good. If it didn't, okay, don't do it. Do something different. Termination, too, can be done however you want. There's no right way to do it. I would say the default way to do it is, hard code, like run for 1,000 generations. Right? Or maybe you say, after a debited? I don't know what that was supposed to say. A desired, probably, fitness value is achieved. That's a typo. Someone can make a pull request to fix that. Impress me. Yeah, termination, after some fixed number of generations, after you find some fitness value that you're happy with, maybe after some diversity threshold is met, maybe the population converged and you're like, diversity is stagnated, I can stop searching. Or maybe if your search has continued and it's been 100 generations since there was any improvement in fitness, you stop it. Whatever you want. It could be whatever. A lot of students have a hard time when it's like, do what you want, but how do I do what I want? By just doing it. Do whatever you want. All right, we'll end here. Any questions? All right, cool.